complex functions. If we take into consideration only the structure of metric space or Nord space, the space of complex numbers, all the complex numbers, that is the space of all the numbers z of the form x plus where x and y are real numbers, can be identified to the real two-dimensional space R2. We identify the complex number x plus y I identified with the vector xy. This is the identification. They are identical as normed spaces, and consequently also as metric spaces. The metric is defined by using the norm. But the space of all the complex numbers has an additional structure, namely the structure of a commutative field given by the multiplication of complex numbers, the number x plus y I, x1, y1, I times x2 plus y2 I is a complex number. The real part is x1, x2 minus y1, y2, and the imaginary part is x1, y2 plus x2, y1, I. This is a big difference. There does not exist anything similar in the real two-dimensional space. For example, we can divide by x plus the complex number in the case when it is different from 0, but we cannot divide by the corresponding vector. The division by a vector is not defined. We cannot not divide by a vector. The space of real numbers is a subset. It can be identified with the subspace of all the numbers of the form x plus 0I, where x is a real number, and it is a subset of the space of all the complex numbers. Let us represent. We know that the geometric representation of the complex numbers. For this, we use the system of axes. And here, this is the space of all the complex numbers. but the space of the real numbers is a subset here, is this red subspace. This is so R is a subset of C. A point here is x plus 0I. Now we want to extend the real functions of real variables outside the real axis. And we shall consider several examples. For example, the function f, the real function of real variable f of x equals x squared, can be extended up to a function up to a complex function of complex variable. Complex function means complex valued function. And evidently the extension outside the real axis, this is the definition for such a point. But if we have a point z here, then the extension is evidently f of z equals z squared, which is evidently z times z. Generally, a polynomial function f of x equals x squared minus 3x plus 1. We can extend this function. This is a function from the real axis to real axis, but we can extend it outside the real axis, and we get the function f of z equals z squared minus 3z plus 1. The restriction of this function up to the real axis is just this function. Now, let us consider another important function. For example, the function defined on R star, which is R except 0, f of x equals 1 over x. The extension of this outside, it is not defined here, this at this point 0. The extension is the function defined on C star. We use this notation for the set C minus 0. And the function is f of z equals 1 over z, defined 1 over explicitly zx plus yi, the real and imaginary part. And in order to find the real part of this number and the imaginary part, we amplify with x minus I, and we get x minus over x squared plus y squared. So we get the real part is x over x squared plus y squared minus y over x squared plus y squared I. This is the definition for this function, which is an extension for this one. And now we intend to extend the exponential function, but for this, firstly, we shall present the definition of this exponential of I t, which by definition, Euler's formula, by definition is cosine of t. T is a real number plus I sine of t, Euler's formula. This definition, with this definition, we have the usual property of the multiplication of two powers having the same basis. For example, exponential I alpha times exponential I beta is cosine of alpha plus I sine of beta times alpha here is the first exponential times for the second cosine of beta plus I sine of beta equals the real part is cosine of alpha cosine of beta. Imaginary unit, you know, this is -1. So we'll have minus sine of alpha sine of beta. This is the real part plus the imaginary part, sine of alpha cosine of beta plus sine of beta cosine of alpha I. But you know that this is cosine of alpha plus beta plus I sine of alpha plus beta. And if we use again Euler's formula, this is exactly exponential I alpha plus beta. So if we have to multiply this to expression, we get this one. By using this formula, we are able to extend the exponential function, you know, from high school, outside the real axis. So the function f from R, the real function of real variable f of x exponential of x, the extension outside the real axis is the function f from C to C, defined by the, we use the same notation, f of z equals exponential of z, where exponential of, for z, let the real part be alpha plus beta I is equals exponential of alpha times beta I. For this we use Euler's formula, so we get here exponential alpha times cosine of beta plus I sine of beta. That is, we get exponential of alpha plus beta I will be, I shall use the same notation as in the other cases, x plus y. I will be exponential of x times the real part, cosine of beta, plus I exponential of x times sine of beta. This is the definition explicitly for this function, which extends the exponential function outside the real axis. If you consider here the case when this point is on the real axis, then y is 0. Then, oh, please, here is y. Then y is 0, cosine of 0 is 1, this is 0, and we obtain the restriction to the real axis is just this function. And now other important functions are the trigonometric functions, sine and cosine. We firstly consider exponential I for this function ix. Euler's formula is cosine of x plus I sine of x, and exponential of minus ix is cosine of x, again minus I sine of x. And from this, if we add these two relations, from this exponential ix plus exponential minus ix equals 2 cosine of x. So we get cosine of x is exponential ix plus exponential of minus ix over 2. We can write the usual function f, you know from high school, the cosine function f of x equals cosine of x can be extended up to a function defined on the whole complex plane, a complex function f of z. We use the same notation, cosine of z, where cosine of z, we can use this expression satisfied for real axis, but you can remark that this expression can be computed when instead of x we put any complex number. So exponential iz plus exponential minus iz over 2. This is the definition, cosine of z. This formula extends the usual function cosine outside the real axis. If z is on the real axis, this formula becomes this one. So you get the usual, the real function cosine. In a very similar way, we have the formula sine of z equals exponential iz minus exponential minus iz over 2i. Sine of z, the extension of the sine function outside the real axis. In certain cases, there are some differences. For example, let us consider the function, the following function, f from R to R, f of x equals 1 over x squared plus 1. This is defined for any real x. This expression is different from 0. We can extend this, but in this case, f of z equals 1 over z squared plus 1. Outside the real axis, we can remark that z squared plus 1 equals 0. From this, we get z12 equals plus minus I. So here, the extension, the maximum domain of definition is C minus, we have to eliminate I minus I from the domain of definition. This is the maximum domain of definition. We have to eliminate these 2 points in order this expression to define a function. We have extended outside the real axis some functions. We can continue. Firstly, we need the following result. Proposition or just definition. For any complex number zx plus y different from 0, there exists a number we denote argument of z in the interval minus pi, such that z, our complex number, can be written as modulus of z times the trigonometric form of a complex number, cosine of argument of z plus I sine argument of z. And if we use Euler's formula, we can write this expression as exponential I argument of z. We have this possibility. In this case, for z, this is the modulus of z, is the distance from z up to the origin. This is the argument of z. If z is, for example, here, then is negative. We choose this interval for this function. This function is discontinuous on this subset. Here is not defined, and here, for example, for a point, when the point tends in that direction, then the argument is almost pi, and here is minus pi, so the limit are different for this. This is discontinuous at this at the points of this set. So we have extended some. Now you know that the natural logarithm is the inverse of the exponential. So we have at least for x a positive x is exponential natural logarithm of x. If we try to identify the inverse of the complex exponential for a z, we have already obtained that is modulus of z times exponential I argument of z. So we can write z. This is a real positive number here for z, different from 0. This is exponential modulus of z times exponential I argument of z. So z can be written as exponential modulus of z plus I argument of z. We have such a formula, but here we can add 2 pi, 2k, a multiple of 2 pi, and the right hand side remains unchanged. So this suggests, if you compare this to define as modulus of z, for the particular choice when k is 0 is the main inverse of the exponential function. This is defined. The real part, if we identify, is natural logarithm of modulus of z. This is real. This is the logarithm from the real case, plus the imaginary part I argument of z in the particular case when we choose k equals 0. But if we choose k equals 1 is another inverse, is a special behavior here. Here to have just an idea on this function. Okay. Now I shall present you an overview for this. Let us an overview. Let us consider here. We started in the previous video clip with the presentation of complex numbers, real part, imaginary part, complex conjugate, modulus, the identification. C is identical to R2 as normed spaces and also as metric spaces. We also remarked that the modulus coincide to the norm, and so the distance in the complex plane between 2 points is given by is exactly the modulus of the difference. The definition of the disk of center Z0 and radius R, convergence to infinity, this fundamental inequality, the convergence of a sequence of complex numbers to this. This happens if and only if the real part tends to alpha and the imaginary part tends to beta. Euler's formula, the representation we have discussed in this video clip. Here are some examples of complex function. Complex function means complex valued functions. The values are complex, and here are some examples of complex functions. We shall investigate in the next video clips the complex derivative, the differential, then the complex integral, properties of the complex integral, and the computation by using the theorem of residues. Okay, now so we stop now here. Thank you.